Okay. System evolving. 1 second. Let me increase the volume. Uh, Control panel. And then so system going. Okay. System sound. Audio device. 1 second. Okay. So now we will start yesterday's continuation. So we have seen in yesterday's class block sort base indexing. Okay. So that comes under index construction. So index construction is a new topic where we will be constructing index and also by keeping in mind the hardware constraints. Okay, so the typical system parameters we will be using for finding out the sorting time. Okay, so let me share this. Index construction. So there, index construction. So we have seen up to this example. So in index construction, in block sort based indexing, we are going to merge the blocks. Okay. So initially, the whole collection will be separated into equal size of blocks, and after that the equal size blocks will be merged based on the posting list. So each posting list will be merged, and finally the whole posting list will be saved in your disk. Okay, so this was explained yesterday. We have Brutus, we have this posting list sorted. We have Caesar posting list sorted. Noble posting list with posting list sorted. So this is of it contains 4 terms, and the second block B2 also contains 4 terms. So this is equal size. This means the two blocks are of equal size. Now these two blocks are being merged here. So the posting list will also be merged. So D1, D3, D6, D7. So for Brutus, it will come here D1, D3, D6, and D7. For Caesar also, it will come here D1, D2, D4, D8, and D9. And for Julius, it remains only D10. It's not there in the other block. And for Noble, it's not there in the other block. So D5, and width it is D1, D2, D3, and D5. So this is how we merge the posting list in block sort based indexing. Now coming to the next slide. So here uh, we have for every this documents we will be having term ID and document ID pair. Okay, so for every, so this is term ID, this is document ID. So the algorithm parses documents into term ID and document ID pairs and accumulates the pairs in memory until a block of fixed size is full. Okay. So we choose the block size to fit comfortably into memory to permit a fast in-memory sort. So when you choose the block size, it depends on you. Okay. So it depends on the user to choose the size of the block. So some user may choose 5 terms in a block, some may choose six in each blocks, or it depends on you. So this is what it is said here. We choose the block size to fit comfortably into memory and to permit a fast in-memory sort. So the block is then inverted and written into the disk. So next one, we have inversion. Inversion involves 2 steps. First one is sorting the term ID and document ID pairs. And next one is collecting all the term ID and document ID with the same term ID into a posting list, where a posting is simply a document ID. Posting is nothing but your location or document ID. Okay, so this one is nothing but the explanation I have done here. Okay, the same thing, this is your term ID, this is your document ID. So we separate the whole document into equal size blocks and you perform the sorting of the posting and also sorting of the terms. Okay, so that means term ID and document ID both should be sorted. And after that, you after merging, we will be getting this as your final posting list. Uh, Then you see to this example, construct be merged using the following document. So I'm using the same document which I have given you in your assignment. 1 second, somebody is joining. So this little piggy went to market. This little piggy stayed at home. This little piggy had roast beef, and this little piggy had none. And this little piggy went all the way home. So it is just a document you can do for many other documents also. What you have to do is there are based on the user, I have separated into 2 blocks. I have separated into 2 blocks with equal size. With equal size. Okay. So equal size means suppose this little piggy went to market. So what you have to write is you can write this here. So that means these terms you separate, distribute into equal number of terms here. Suppose if you have 10 terms here, you have 10 terms in your block 1 also. If you have 8 terms in block 1, then 8 terms in block 2. So here we are considering all the stop words. We are considering all the stop words here. So one example I'm writing here, and it is there in D5, all it is there in D5, and it is there in D2. So just 2 numbers I'm giving. Say 1 second. So we are starting with the sorted one, right? N. So next one is after A, B, C, D, E, F, then G, H. Okay, so next one will be had, like this. Had is there in D3. So you can put the other had here in D4, like this. Okay. And when you distribute the terms, it should be of equal size. Okay. And also in the sorted form. For example, if a had is there in D1, Both the hats are there in D1, then you can write D3 and D4. So you can exclude this hat. Okay, so I'm just taking two examples now. So here also I have two terms. Here also I have two terms. Okay, so now it is of equal size. My block 1 and block 2, they are of equal size. Now this has to be merged. So when you merge here in the this side, it will come all D5 and D5 at D2, then at D3 and D4. So at D3 and D4, like this. Okay. So you can just do by yourself this one. Refer the example given here. So refer this example and you can solve this one by yourself. Okay. So this is about block sort based indexing. Now coming to next one, distributed indexing. Distributed indexing. So we will see up to distributed indexing today. One second. So distributed indexing. So here again in block sort based indexing we find some issues or some inconvenience while performing the sorting process. So that's why we will be again using distributed indexing. And in distributed indexing, map and reduce scheme is the uh, important one which we will be solving now. Okay. So before that, let us see from here. Block sort based indexing. It needs data structure for mapping terms to term IDs. This won't fit in memory for big corpora. That means large and structured set of text. Okay, so that means what? So it needs a data structure because for there will be a mapping, right? Term ID, document ID, term ID, document ID, mapping will be there. So if the size of the collection is large, then we cannot fit into memory. The mapping process cannot be fit into the memory for large collection of text or data. That's why initially before moving on to the distributed indexing, we first follow a technique which is known as single pass in memory indexing. Okay, single pass in memory indexing before we go for distributed indexing. Okay, so initially we perform inverted indexing, that is sort based indexing. Okay, so initial thing was sort based indexing, and sort based indexing also we find some disadvantages on it. So we go for block sort based indexing. Again, for block sort based indexing also there is mapping for term ID and document ID. So if mapping can be done for smaller sets of data, but when it becomes very large, then this won't fit into the memory. That's why we again use a technique known as single pass in memory indexing. So this one will be dynamically creating dictionaries. Okay, in single pass in memory indexing, we will create dictionaries dynamically, and it will store dictionaries means the terms. Okay, we will store the terms with the blocks and integrate sorting and merging. So this is what we do in single pass in memory. That means we can create dictionaries dynamically, and also we can store the dictionaries or the terms with the blocks. After storing it, we can integrate both sorting and merging once at a time. Okay, here the advantage is we are integrating sorting and merging at the time. But in block sort based indexing, what was the process we have done? We have done sorting first and then merging later. So individual memory allocations has to be created, right? So in single pass in memory indexing, we do not create different memory blocks for sorting and merging. We integrate both sorting and merging in the block itself without separating. So this is one of the advantages of single pass in memory. So there are some steps here. Generate separate dictionaries for each block. No need to maintain term ID and document ID mapping. Okay, maintain term ID and one is term ID, one is document ID. Mapping terms to term ID. Sorry, that is not a document ID. Mapping terms to term ID. So what I have said was term ID and document ID mapping. No, it is terms and term IDs. So it was a mistake. You just check here. Terms and term ID. What do I say here in your initial example? A term can be given some term IDs, right? So if Brutus is there, you can give BR. So a mapping should be done. A mapping should be done for each term if we want to create term IDs, right? So this, when the number of terms is more, then it will be difficult to fit into the memory. This is what it is said here. Okay, not the term ID and document ID mapping. It is the mapping of the terms to term ID. Okay, it is the mapping of the terms to term IDs. So here we can create or we can generate separate dictionaries for each block. So here we don't need to map term and term IDs across the blocks. Okay, we don't need to create term ID and term mapping. So no sorting, accumulate posting in posting list as they occur and generate a complete inverted index for each block. These separate indexes can be merged into a big single index. So that means individually we will be performing all the process what we have done in block sort based indexing in a separate block. And after performing all the posting list or after constructing the final index in a single block, then the remaining blocks we can merge into a single one. So here, okay, this is what we have done in the previous example. So for Brutus, Caesar, Julius scale, all the terms in this block, we will perform the posting list here and we will perform everything in a single block. Here also in this block, whatever it is there, we will perform the posting list and finally all this will be merged into a single block. Okay, so once again let me explain this. So block sort based indexing, it needs a mapping of the terms to term IDs because for larger set of strings and if the length of the string is more, we create a term ID for the terms. So a mapping is necessary for uh, converting the terms into term ID. So when the number of terms is more, this won't fit into the memory. Okay. That's why we move on to single pass in memory indexing. So in the memory itself, we will perform the indexing. Okay, so initially what we have done was we have done sorting separately, merging separately, and finally indexing is done and saved in the memory, right? But here in the memory itself, we will perform sorting, merging, indexing, and finally a big index can be created after we complete its block indexing. Okay, so that is what it is said here. In memory itself we perform the indexing. Okay, now so since we perform the indexing in the memory itself, we do not require mapping of the term and term IDs, and also no sorting will be done because it is integrated with merging. Merging and sorting is integrated, so no individual sorting will be done, and it is already accumulated as they occur. Okay, so no individual sorting, it is an integrated sorting and merging in the memory. And finally, we have distributed indexing. Okay, so why we perform distributed indexing? It is nothing but index construction. Performing index construction is very difficult if we perform in a single machine. Okay, when the collections are very large. So when the collections are very large, we will find difficulty in index construction if performed in a single machine. So we need several machines, right? We need several machines to perform the indexing process. That's why we have used distributed indexing so that it will be distributed across several machines, and we can perform the indexing process. So it is said here, you see, a collections are often so large that we cannot perform index construction efficiently on a single machine. Okay, on a single machine we cannot perform when the collection is very large. Constructions will be very difficult. Index construction will be very difficult. So we need a distributed index that is partitioned across several machines. So we need a distributed index that is partitioned across several machines, either according to the term or according to the document. Clear? So instead of performing the index construction on a single machine, we are going to use several machines being partitioned across. So that process is known as distributed indexing. That means indexing we are going to perform in several machines and link together, and finally we'll get a single result. So map and reduce. In distributed indexing, we use map and reduce architecture. Map and reduce is nothing but an architecture for distributed computing. So this architecture we will be using for distributed indexing. So map reduce, it breaks a large computing problem into smaller parts by recasting it in terms of manipulation. So here we will use key value pairs. Key value pairs. So we'll see the example. One more explanation. Map phase of map reduce consists of mapping splits of the input data into key value key pairs. So mapping split of the input data into the key value pairs. That's reduce function. It is what we are going to do. Given values for a given key will be stored close together so that they can be read and processed quickly. So you see this. So after seeing this only you will understand what is map reduce architecture. Okay, so this is the function of map and reduce. We have a schema of map and reduce. Finally, see here, map is nothing but the input. We are going to take the input. Your input is what? List of key value pairs. Okay, KB is nothing but key value pairs. So map is nothing but we are going to take the input and list is input is nothing but your key value pairs. Then reduce function. Reduce function is we are going to process the keys along with the list of values and we will get the result. Okay. Once again, map function is for taking the input. And what will be your input? Your input will be list of keys and value pairs. It should be in the form of pairs. So key and value is nothing but key will be your term ID, value will be your document ID. Okay, once again, key will be your, K will be your term ID, V will be your document ID. So pair, key value pair. That means term ID, document ID pair. Then in reduce function, you will have your key, that means your term ID, and list of your document IDs. The list of V, the second line you see here, list of V is nothing but your term ID, list of document IDs. List of document IDs. Okay. Now you see the example given here. Map. Map is input. Input, we are taking the web collection. Input, we are taking from web collection. And our input will be list of term ID and document ID. Rakesh Wangkhem di chang tengah isi kaigino why Rakesh Wangkhem. So this second part, you see the second line here, map web collection. It is a web collection and our input will be in the form of list of keys and values, term IDs and document IDs. So that is what it is written here, list of term ID and document ID. Now coming to the reduce function, in reduce function, it is key and list of values. Key is your term ID, list of document IDs. So term ID 1, list of document IDs. List of document IDs. So term ID 1, list of document ID. Term ID 2, list of document ID. And this will return you the posting list. This will return you the posting list. Now come to the third line. Example for index construction using map and reduce. Example for index construction using map and reduce. So map function is nothing but your input. The input it will take in the form of list of keys and values, list of term ID and document ID. So document ID and term ID. Term ID and document ID. So map function, this is nothing but your input. So I have document 1, I have document 2. In document 1, C conquered. So C is nothing but Caesar. We are just writing the ID. Instead of writing Caesar, we are writing C. Instead of writing conquered, we are writing C apostrophe ED, conquered. Okay. So C is Caesar, then died. So D1 and D2. I have two documents in our input. So our input contains two documents. First document is Caesar came, Caesar conquered. And in document 2, we have Caesar died. Two information. Okay. Now, if we have to write this in the form of term ID and document ID pair. Term ID and document ID pair. So C is your term ID. C is there in D2. Okay. C is there in, that means Caesar is there in D2. Then, so we are starting with document 2 because it is written here with the document 2 first. So I'm starting with C, this first C here. Caesar C is there in document 2. So term ID, document ID. Now second what is, second term is died. Term ID, document ID, D2. Then you come to the next D1, C came. That means Caesar came. So C D1 came D1, C D1, conquered D1. Okay. So we have written down D1 information and D2 information in the form of term ID and document ID pairs. Term ID and document ID pairs. So for map function, this is the input. Term ID, document ID, term ID, document ID, term ID, document ID, and so on for all the terms and their respective document IDs. Now coming to the reduce function, in reduce function, here what's your this schema? K list of V. K is your key is nothing but your term ID. List of V is nothing but values are document IDs. So I'm writing K, which is your term ID here. Term ID is C, that means Caesar. So this is list of document IDs. D1, Caesar is there in D1, Caesar is there in D2. So I'm writing Caesar is there two times, right? D1 here also, here also. So I'm writing D1, D1, D2. And for died, also, I'm writing D2 here, list of document IDs, that is D2. That is there only in D2. Now, came, it is there only in D1. Conquered, it is there only in D1. So, I have written down here in the form of K list of V. K list of V. K list of V. K is term ID, list of document IDs. Term ID, list of document IDs. And final output will be like this. You see here, our final output is our posting list, right? So Caesar, this is your term ID, document ID D1. In D1, Caesar is there two times. In D2, Caesar is there one time. And died, it is there in D2 one time. Came, it is there in D1 one time, along with the frequency we are writing here. Conquered, it is there in D1 one time, like this. This is the function of map and reduce. So you can do this example by yourself. Document 1 English tutorial fast track. Document 2 English learning fast tutorial. So you can perform map and reduce function here. This is your map. Map is nothing but term ID document ID list. Reduce is nothing but term ID list of document IDs. Term ID list of document IDs. So you apply this two function map and reduce schema on these two given documents and you will get the result. For map, this is the output we get. That means for mapping function, this is the result we get, and for reduce function, this is the result we get. So you do it by yourself and check it if you get the same result. Okay. So this is about distributed indexing. So I think I cannot start a new topic. So for today, let us wind up with this example. So let me take a roll call. Once again. Roll number one,
Present, ma'am.
roll number two,
Present, ma'am.
roll number three,
Present, ma'am.
roll number four. Sorry, roll number five,
Present, ma'am.
roll number six,
Present, ma'am.
seven,
Present, ma'am. Present, ma'am.
eight. Daya Sagar, roll number nine,
9 present, ma'am.
10,
Present, ma'am.
11,
Present, ma'am.
12,
Present, ma'am.
13,
Present, ma'am.
14,
Present, ma'am.
15,
Present, ma'am.
16,
Yes, ma'am.
Present.
17, Gyanendra, 18,
Present, ma'am.
19,
Yes, ma'am.
20,
Present, ma'am.
21, Keshav Kumar, 22, 22 Jackson Koizam, 23, Pravin, 24, Nishita,
Present, ma'am.
25,
Present, ma'am.
Present, ma'am.
26, 26 Lavisha, 27,
Yes, ma'am.
28,
28. Yes, ma'am.
29, Mayank, roll number 30,
Present, ma'am.
31,
Present, ma'am.
32, roll number 32, roll number 33,
Present, ma'am.
34,
Present, ma'am.
35,
Present, ma'am.
36,
Present, ma'am.
37, Vishnu,